Okay guys, so what we're going to be doing here is we're going to kind of build on the idea that we talked about previously where we were talking about velocity, where we're going to look at it more in a slightly more AP context, if you will. The problems that we're going to be looking at here, the ideas we're going to be looking at, we're actually going to break this into two different parts. So this video, there will be a video today, and then there'll be a video, the second part of this video. You can watch them together, whatever. But know that the ideas that we're talking about here are fairly unique to what you might see on the AP test. They're not unique to calculus other than the way that they are written. And so in order for us to understand these particle motion problems that we're about to be looking at, we have to know a few definitions. The first definition that we're going to talk about is what is known as displacement. Now, displacement, as you can see here, is simply how far an object is from where it started over a given time interval, okay? Usually the biggest issue that people have when they're trying to decide, that when they're looking at problems like this, is deciding the difference between displacement and the distance traveled. Displacement does not take into account anything that happened other than the beginning time or the ending time. So, like if I'm going on a trip, let's say or not on a trip, but let's say I'm going to go like on a day trip where I go and maybe I visit like the Great Salt Lake or something like that. Well, I go out there, the Great Salt Lake's about 45 miles away, give or take. So I go out and I visit it, and then I go and I come back home. I've traveled 90 miles. So like my total distance that I traveled would be 90 miles. But my displacement, because I only look at the beginning of the day and the end of the day, would be 0. And so there is a difference between them. And luckily for us, they're not like super difficult to discern. They work a little bit differently as we get much further into the year as far as how you find them. But it's nothing to worry about right now. In fact, we have a formula that we use to find the displacement. You'll notice here that the formula for displacement is S of B minus S of A. And if you remember from our previous discussion, what S is that is the formula that tells us how to find the position at any given time. So basically this is saying find the position at the end of the time interval that you're interested in, find the position at the beginning of the time interval, and subtract the two. Now, one mistake that I see that gets made often when we're talking about displacement is people forget to find where the object was at the beginning of the time interval in question, especially when the time interval starts at time equals 0. Just because we're talking about an object in motion doesn't mean, and we have a formula for it, doesn't mean that it always starts at an original place. It's not always a position time equals 0. And we'll see that as we look at a couple of problems we get a little bit further into this, okay? Now, average velocity, which we've talked about before, the actual definition for average velocity is you find the displacement and then you divide that by how long it took for that displacement to occur. So if I saw a problem like this, if a particle has displacement, and that was just found by, again, taking the ending point and subtracting the beginning position off of it, so ending position minus beginning position, it says that that is 10. If I were to, and we'll say that's in meters, as it says in the problem. And then if I were looking at this, that's from time equals 2 seconds to time equals 7 seconds. Hopefully you can see that 5 seconds has elapsed. So if I wanted to know the average velocity, it's kind of like what you used to do velocity problems. You would just have 2 meters per second, because 10 divided by 5 is 2. So that would be our average velocity of this particular particle. Now, when we talk about particle motion problems, what we're basically talking about is an object that is just moving in one dimension. In other words, it's either moving to the left and right, and that's all it's doing. And that's kind of what you see here on this picture of this GIF that was made. Just shows a particle moving backwards and forwards. So it's moving back and forward and back and forward. And you can see that it's only moving in one dimension. It's not moving up and down at the same time. If you take Calculus BC, we talk about what happens if we talk with particles that are moving in two directions. But that's not something we have to worry about right now. So we're just talking about this particle moving backwards and forwards along the x-axis like this one is right here. Now, as a quick reminder, a velocity in a particle motion problem, velocity in general tells us two things: how fast we're going and the direction in which we are headed. So in a particle motion problem, if we have a positive velocity, that either means, since we're only moving in one dimension, that you are either moving up or you are moving to the right, depending on what that one dimension is. If I have a negative velocity, then that means you are moving either down or to the left. Okay? So again, what we have to remember is when we use the word velocity from here on out, we are talking about the derivative. We're talking about an instantaneous rate of change. So if I take the velocity and I plug a number into it and I get negative 41, what that means is that it's moving in a negative direction at 41, whatever the units are, meters per second, or whatever that is. Now, acceleration, and there's a demonstration that I kind of use, and I'll explain it as best I can here. Acceleration it tells us the direction in which the force is being applied to an object. It is never the direction in which the object is traveling. So say we had this block here, okay? And if this block were moving in this direction, so if it were moving to the right, we would say that it has a positive velocity, just due to the fact that it is moving to the right. And if it is moving to the left, then we would say that it has a negative velocity, solely based on the fact that it's moving to the left. And we talked about that before. Now let's say we were able to wrap like a band or something around this block. So I'm going to wrap a band around it. And once I wrap that band around the block, there's an extension of the band either in this direction or in this direction. Now, if somebody were to pull on the band in this direction, so to the right in this case, we would say that we have a positive acceleration. That just means that the force that is being applied to this particular block is in that direction. Somebody's pulling on it with a band, and it's not necessarily, and this is the part that people struggle with, it's not necessarily causing the band to move in that direction, but there is a force that is pulling in that direction. We'll talk about that in just a second. Meanwhile, if somebody's pulling on the other side, then we would say that we have a negative acceleration. Now, in general, in these problems, you don't have both being applied at the same time. It's either one force is acting upon the object or the other, but not both at the same time. So what is happening here is we can say, okay, I've got a positive acceleration if the force is moving in this direction. If the force is moving in that direction, we have a negative acceleration. Now, on the AP exam, what will happen is we will say, okay, we have an object that is moving in one direction and an acceleration that is maybe moving in another direction. And so what we have to determine is whether or not an object is speeding up or slowing down based solely off of what we see from our acceleration and our velocity. So if I were to find the acceleration, remember that is the second derivative, and I were to use the velocity function, that is the first derivative, and I were to plug a given time into both of them. If I got both a positive velocity and a positive acceleration, we would say that the object in question that we are talking about is speeding up. Because not only are we walking in the direction, so in this case, that would be to the right. So not only are we walking in the direction that with a positive velocity, so that means we have a positive, but something is pulling me in that direction as well, which is causing me to speed up because it's like they're working together. The same thing would be true if I had a negative acceleration with a negative velocity. Both of those would be working in tandem, so they'd work together, even though they're both negative, because they're both, remember, negative just means that is the direction in which the force is being applied, and that is the direction in which we are traveling. So as long as the force and the direction you're traveling are the same, then you're going to be speeding up. Whereas, if I had a negative acceleration, but a positive velocity, it's like somebody's pulling on the band in this direction, but you are walking in the other direction. So I'm walking towards the right, but I'm being pulled towards the left. That would mean that I am going to be slowing down because they're not working together. And the same thing would be true about a negative velocity and a positive acceleration. So in these problems, you have to watch out to make sure that when you're asked these, to not just automatically make assumptions about one or the other. You have to compare both the velocity and the acceleration. So let's look at an example that's kind of tie all of this together right now. Let's say I had a particle moving along the line x equals 2. Now what that means is I've got the line x equals 2. So if I were looking at a graph, x equals 2 is just this line right here. Like that's what that line kind of looks like. And then we've got a teeny tiny dot, that's why they call it a particle, that's moving along this line. In other words, it's moving up and down, up and down, up and down. And this equation that we have right here will tell us where this particle is at any given time on the line. It'll tell me the y value at any given time. So it's a position equation that we are looking at. So if I wanted to find the position of the particle, what I would do is I'd say, okay, that's what this formula tells me. At a specific time, I would say 2 times 3 to the third minus 21 times 3 squared plus 72 times 3 minus 53. And we would just plug that right into our calculator. And when we do that, we get 28 as our position. So I get 28 right here as my position. Now again, that just means on this line, I'm 28 units above the x-axis, 28 units up. Now if I needed to find the displacement, I couldn't just take the position at time equals 3 and divide it by 3, because they're not the same. Sorry, I was getting ahead of myself. I couldn't just say 28 is the displacement as well. Even though I am 28 units away from the x-axis, my displacement, I would need to find out where I started by taking my position equation that I have and plugging in my starting time, which in this case would be 0, because I'm going from 0 to 3. So when I do that, I plug in 0 and I get negative 53. That would be my displacement after 3 seconds. My average velocity then, oh wait, excuse me, I'm not done yet. That is my position at time equals 0. This is my position at time equals 3. So in order to find out where I was, I would go my displacement, I'd go 28 minus negative 53, which is 81. What that means is I am 81, whatever the units are, away from where I started, because I did not start at 0. My position was not 0. So if I wanted to know the average velocity, what I would have to do is I would have to take 81, and because that's my displacement, and I would divide that by 3, which gives me 27, it'd be like meters per second or feet per minute or something like that. That would be my average velocity over the first 3 seconds. Now, if I was looking at this, notice again I've got my position equation. If I want to know the velocity at time equals 5 seconds, notice that's asking for the velocity at a specific time. What that means is because it's at a specific time, it's an instantaneous velocity, which means we are going to use our derivative to find out the velocity at that time. So I'd go 6 times 5 squared minus 42 times 5, because that's what the derivative tells us of position. And again, I would just plug that into my calculator, and that would give me, 12 as my answer. Okay, and again, that would be like meters per second or feet per minute, whatever it is. That would be my instantaneous velocity, or my velocity at a given time. The acceleration, as we talked about last time, is simply, the way that we find it, is we take the first derivative of velocity, or the second derivative of position, and that gives us this particular formula. So if I wanted to know the acceleration at time equals 2 seconds, I would go 12 times 2 minus 42, which would give me negative 18. Now, again, what that means is the force is pulling in a negative direction this time. So I'm being pulled to the left, or down in this case, as we're talking about moving up and down across this line. Now, if we wanted to find out whether something was speeding up or slowing down, what we would have to do here is we'd have to say, okay, this is a slightly different question than what I was being asked before, because I need to find out whether I'm speeding up or slowing down, which means I need to know both the acceleration and the velocity at a given time. So like at time equals 1, I would take 1 and I would plug that into my velocity first of all, and that would tell me how fast I was going and the direction in which I was headed. So in this case, when I plug that into my calculator, I get 36 as my velocity. Then I take that same time and I plug it into my acceleration. And when I do that, I get negative 30. Again, we don't have units associated with these right now, and that's okay. So notice I have a positive velocity, which means I'm moving to the right, but a negative acceleration, which means something is pulling me to the left. So that, in this particular instance, I would say that this is slowing down. Now, in the interest of time, on the other two, on time equals 6, if you want to try that one on your own, you're going to get that they are speeding up. In this case, both the acceleration and the velocity are positive. And then at time equals 3, this one's actually kind of interesting. At time equals 3, when I plug that into my velocity formula, 3 plus 72, I actually get 0 for my velocity. If we have a 0 velocity, that means that we're not moving in either direction. So it doesn't matter if somebody's pulling us in either direction. At that instant, we're not moving in one direction or the other. So we would say that we are neither speeding up nor slowing down. And again, that doesn't happen very often, but it does happen in this case. Now, don't forget, this is just part 1 of part 2. So if you have any questions about this one, let me know. We will continue talking about how to read graphs to determine these types of things in the next video. So again, if you have any questions, please ask.